Bismillah ar-Rahman ar-Rahim. Processors and microcomputers. What is a microprocessor? A microprocessor is a digital integrated circuit that can be programmed. It can be programmed with a series of instructions to perform a specific function on data. Okay. That leads to the question, what is a program? A program is a series of instructions that are logically ordered in order to perform a specific task. Okay, then what is an instruction? The instruction is a series of zeros and ones that the microprocessor understands by hardware. The designer designed the microprocessor to understand this series of bits, a fixed series of bits, as an instruction. Alright, the microprocessor does not work alone. It has to be part of a system. That system might be called a microcomputer. What is a microcomputer? It's a system that consists of a microprocessor and memory units, for example, read-only memory, read-write memory, hard disks, input circuits or input ports, and output ports. What are the input ports or input circuits? They are internal circuits to the microcomputer that connect peripheral devices, peripheral input devices, like a mouse, for example, is connected to an input port. A keyboard is connected to an input port. The output ports, they connect output peripheral devices, like a printer, for example, like a monitor, a data show. Now, all these devices, the input ports, output ports, memory, they are connected to the microprocessor via what's called a system bus. What is a system bus? It will be explained later. But it's a group of wires that allow for the communication between the microprocessor and these devices. And this is called a microcomputer. What do we see inside the microprocessor? What are the basic elements for the microprocessor? Inside the microprocessor, there are four major subdevices or subsystems. First of all, something called the arithmetic logic unit, abbreviated as ALU. What does the ALU do? It performs all the arithmetic and logic operations. And we know that the program actually is a set of arithmetic and logic operators that have to be executed. So the ALU executes arithmetic and logic operations. Now, in order for the ALU to perform arithmetic and logic functions, it needs a register array, a set of registers where the operands have to be stored temporarily. Suppose that the ALU wants to add two numbers, number A and number B, and get a result which is C. So it needs a register to store the first number, which is A, and a register to store the second number, and register to store the temporary addition of the two. So there must be a register array, which is a set of registers used by the ALU. Okay, the third part of the microprocessor is the instruction decoder. The instruction decoder receives the instruction from the memory, the instruction to be executed, and it decodes it. Somebody has to understand what this series of bits coming from memory mean, and this is the instruction decoder. The instruction decoder, it understands, it decodes the instruction that the microprocessor gets from the memory, and then it passes this instruction to the control unit so that the control unit perform the hardware signals necessary to execute the instruction decoder. How does the control unit do that? For each instruction, the control unit issues a set of timing and control signals to the surroundings so that the instruction which is received is executed. This set of timing and control signals issued by the control unit is called a microprogram. Each instruction has its own microprogram that is generated by the control unit. Okay, the main task for the microprocessor is to execute a program. This is the task of the microprocessor, execute a program. Okay, how does the microprocessor execute a program? It does that by repeatedly cycling the following steps. These are called the basic operations of the microprocessor. First, it has to fetch the instruction from memory. The instruction is stored in memory as a series of bits. This is called the operation code. It has to fetch the operation code from memory, and this is called opcode fetch. Now, it passes this code to the instruction decoder so that it decodes it, and then the instruction decoder passes this to the control unit to perform the execution, and then writing the result where the instruction requires. So the four basic operations that the microprocessor do in order to perform the execution of the program are opcode fetch, decode, and then execute. This is for every instruction. Now there is something called the instruction set. The instructions set. Each microprocessor is designed to understand a certain set of instruction. It's the set or all the instructions that the microprocessor understands by the hardware design. Right? This is called the instruction set. It doesn't understand anything else. Now there's something called the word. The word is the number of bits the microprocessor recognizes and processes at a time, and this has to do with the data bus size for the microprocessor. Alright, it can, suppose that the microprocessor can process 8 bits of data at a time. That means it can store 8 bits of data in memory, or it can receive 8 bits of data from memory. Then we say that the word size for this microprocessor is 8 bits or 1 byte. If it can handle 16 bits receive 16 bits or store 16 bits, then we can say that this microprocessor is a 16-bit microprocessor. Okay, machine code and assembly language. Suppose we need an instruction that should do the following: set W register to F7. There is some register called W in the microprocessor, and we need to put F7 in this register. When the designer designed the microprocessor, this set of bits perform this instruction. Whenever the instruction decoder receives this set of bits, this is for the PIC16F877A microcontroller, which has a 14-bit instruction length. Okay, this is understood as set W register to F7. Okay, when the instruction is in this format, it is understood by the microprocessor. It is in the machine format that the microprocessor understands. We say that this is in machine format instruction. Okay, but this is hard to deal with. It's easier if we put it in this format, in hexadecimal format: 7 F 0 and 3, assuming that the x's here are zeros. So this instruction is put in hexadecimal format, but still it is hard to program using this format. Anyway, this format, if the program is in this format, we say that it is in the machine language format. It's in the format that the machine understands. Okay, but we can write this instruction in a different format. For example, we can say, what does this instruction do anyway? It puts F7 into the working register. Okay, what happens if we say move this literal, which is F7, into the working register? Move LW F7. Then we have a language called assembly. This is an assembly format instruction. We can say move LW F7. It has some meaning, and it's easier to program with, because now I can say move LW 33 to put 33 in the working register instead of F7. Alright? The instruction written in this format is written in the assembly language format, and this is said to be the mnemonic format, and the M is silent. Mnemonic format. Our PIC has a set of 35 different instructions in assembly, and each instruction is 14 bits. So now we understand the difference between assembly language and machine language. All right, but you told us that the microprocessor does not understand except what it is designed for. That is machine language. At the end, you have to have the program written in the machine language, and now we're using assembly. So you must convert this assembly into machine language format, and that is done by using something called the assembler. The assembler is a program that understands the assembly format and then converts it into the proper machine language for that specific microprocessor, because each microprocessor, it has its own fixed series of machine language instructions. You put your program, which is the source program, in assembly format. Suppose if you write a program, call it X, all right, and then you give it an extension ASM to give it to the assembler. The assembler will produce a file called x.obj, which is the object, which is in the machine language format that the microprocessor you're working on understands. All right, the computer consists of two parts, a hardware part and then the software part. The hardware part is anything which you can touch. The microprocessor is the hardware, memory, all types of memory, disk drives, input devices, anything that you can physically touch is called hardware. But the hardware is nothing without the software that is running on this hardware. All right, so we have the software part. We saw that the hardware understands only machine language software, all right, and each microprocessor understands its own machine language software. All right, so if we wrote in assembly, we needed an assembler to convert it to the machine language in order to control the hardware. But now we have another form of software. We have high-level language. We can write in C++, for example, in Java, in Oracle, what have you. But still, it has to be converted into machine language format, and this is done using compilers or interpreters. We called C++, Java, Oracle, we call that high-level language. It has certain specific characteristics. Assembly and machine language are called low-level languages. So we have high-level language and we have low-level language. What are the differences between these? We will see later on. Now the compiler converts the source program that you wrote in high-level language, for example C++, into the machine language in an object program, machine language program that is suitable for the computer you are working on. Okay, when you write in high-level language, C++, for example, you really don't care what the microprocessor, the compiler that you use will worry for that, will take care of that. It will convert your source into the proper machine language for that microprocessor. If you change the microprocessor, the compiler, you have to recompile again, right? And then you will get a different object code than the one you got here, because this microprocessor is different than this one. So each time you move your work to a different computer, you have to recompile again in order to get the proper object code for the specific microprocessor. So we can see that the C++ does not depend on the machine that you're working with. You do not worry in your programming about the machine. You just write the same C++. Assembly versus high-level language. What are the characteristics of the two types of programming languages? In assembly language, we saw that it is machine dependent. The assembly or the mnemonics for the 8085, for example, are different from the mnemonics for the 6800 microprocessor, as an example. Each microprocessor has its own set of instructions, so you have to know for what microprocessor you are programming. So it is machine dependent. While we saw that the high level language, C++, for example, is machine independent. We do not care about the microprocessor that the program is written for or is going to run on. The assembly is used to write small applications, while the high level language is used to write large applications. It's easier to deal with, it's easier to debug or maintain. That's why it is used for large applications. The assembly language is more efficient in programming because it's closer to the hardware. The assembly language is more efficient than the high level language, but it requires less memory. You can run a program on a computer which has low memory if you write in assembly, while you need to have high memory in your computer if you want to run Oracle, for example. The instructions here are called mnemonic. Here the instructions are English statements, as you know. These are the differences between assembly language and high level